Section: Introduction. In this section, we discuss the impressive abilities of large language models, LLMs, across various tasks. To effectively use LLMs in different applications, prompts are crucial as they guide the model's behavior and ensure the outputs meet user expectations. We identify two types of prompts: system prompts, which provide general instructions applicable to many tasks, and user prompts, which are specific inputs aimed at addressing particular queries. As LLMs improve, the effectiveness of their performance is closely tied to the prompts we provide, leading to increased interest in creating effective prompts. Traditionally, we have relied on manual prompt crafting, which has produced useful prompts like chain of thought that enhance reasoning. However, this manual process is time-consuming and not easily scalable. To address these challenges, automatic prompt optimization has emerged, aiming to enhance prompts using LLMs or algorithms to explore better variations. Notable methods include textual gradients, which generate feedback on prompts based on model predictions, and Monte Carlo tree search, which evaluates different prompt configurations. Despite the focus on user prompts in prompt optimization studies, we recognize that system prompts are equally important in shaping LLM behavior and can influence responses across a wider range of contexts. Optimizing system prompts offers several advantages. They provide stable instructions that can apply to multiple tasks, and they create a strong framework that helps LLMs adapt to new user prompts and domains while working well with them. To fill this gap, we introduce the concept of bilevel system prompt optimization, which aims to create system prompts that work effectively with various user prompts and can generalize across many tasks, including those not encountered during optimization. Unlike traditional methods that only optimize user prompts, our approach faces unique challenges as it requires simultaneous optimization of both system and user prompts. We frame this as a bilevel optimization problem, where the system prompt serves as the higher-level objective and the user prompts as the lower-level objective. We propose to address this problem using a meta-learning framework, which is ideal for learning from a range of tasks rather than just individual queries. This framework allows us to meta-train the system prompt over diverse user prompts and tasks, enabling it to generalize to new instances. By iteratively updating user prompts within the meta-learning loop, we ensure that the system prompt is optimized alongside various user prompts. This meta-learning approach has several benefits. It outperforms non-meta-learning methods in handling unseen prompts and tasks, which are common in real-world situations. Additionally, it is versatile, allowing for the integration of various prompt optimization techniques. We call our method the Meta-Level System Prompt Optimizer, or Meta-SPO. We validate our Meta-SPO framework on 14 unseen tasks across 5 different domains in 2 real-world scenarios: unseen generalization, where the optimized system prompt is tested directly on queries without further user prompt optimization, and test time adaptation, where user prompts are optimized with a few examples while keeping the system prompt fixed. Our results show that in the unseen generalization scenario, the optimized system prompt significantly outperforms baseline methods, demonstrating strong generalization across diverse tasks. In the test time adaptation scenario, the optimized system prompt also enhances user prompt optimization, leading to quicker convergence and better performance. Section Summary. In this section, we discuss the critical role of prompts in guiding large language models, LLMs, and introduce the concept of bilevel system prompt optimization, which aims to enhance system prompts for better generalization across diverse tasks. We propose a meta-learning framework, Meta-SPO, that optimizes system prompts in conjunction with user prompts, demonstrating superior performance in both unseen generalization and test time adaptation scenarios. Section: Related Work. In this section, we discuss related work on system prompts and prompt optimization in large language models, LLMs. System prompts, which were introduced with ChatGPT, are essential for shaping the behavior of modern LLMs. As we see more studies on system prompts, we find that adding a persona can improve LLM performance in role-playing tasks. Some recent research has also suggested training methods to better align models with various system prompts, focusing on following the most important instructions. However, while these studies concentrate on aligning models to predefined prompts, our work aims to automatically optimize system prompts. Prompt optimization is crucial because LLM performance is highly influenced by the quality and structure of prompts. Early research used gradient-based methods to adjust a few trainable parameters, but these methods are costly and not suitable for closed-source models. To overcome this, gradient-free methods have been developed, which generate and evaluate candidate prompts iteratively to find the best one. Some approaches also analyze the current prompt before creating optimized versions. Additionally, evolutionary algorithms have been applied to optimize prompts. Despite these advancements, most studies have focused on user prompts for specific tasks, with limited attention to system prompts. Recent work on system prompts has either been limited to safety tasks or has not considered interactions with various user prompts, even though an optimized system prompt should work across different tasks. We aim to fill this gap with a new approach to bilevel system prompt optimization using meta-learning. Meta-learning, or learning to learn, seeks to gain knowledge that can be applied across various tasks, allowing models to adapt quickly to new tasks with little training. For instance, model-agnostic meta-learning learns a shared starting point that enables quick adjustments for different tasks. Other methods represent task distributions in an embedding space for adaptation. While meta-learning has been applied to prompt optimization, previous works have mainly focused on gradient-based methods, which differs from our emphasis on gradient-free techniques. Moreover, meta-learning has not yet been explored for optimizing system prompts. We begin our methodology by explaining the basics of LLMs and traditional prompt optimization techniques. We then introduce the challenge of bilevel system prompt optimization and present our meta-learning-based solution. Formally, LLMs take an input that includes a system prompt, a user prompt, and a specific query, generating an output. The system prompt provides general behavioral guidelines, the user prompt specifies the task, and the query contains the input needing a response. Given the sensitivity of LLMs to prompts, prompt optimization aims to automatically find prompts that enhance task performance through iterative refinement based on feedback. We define a task as a dataset of input-output pairs, where the goal is to identify the best user prompt that maximizes performance. Previous studies have focused on optimizing user prompts, but this has limitations. User queries are often drawn from a single task distribution, making it hard to generalize to new tasks. This means we often need to re-optimize user prompts for each new task, which is inefficient. Additionally, while system prompts can serve as universal guides for LLMs, previous methods have largely ignored them in the optimization process. By focusing only on user prompts, we miss the opportunity to leverage system prompts to enhance LLM performance in a more general way. Section Summary. In this section, we discuss the significance of system prompts in large language models, LLMs, and highlight the emerging field of prompt optimization, which traditionally focuses on user prompts but often neglects system prompts. We propose a novel approach to optimize system prompts using meta-learning, addressing the limitations of existing methods that fail to generalize across diverse tasks and interactions with user prompts. Section: Bilevel System Prompt Optimization. In this section, we introduce the concept of bilevel system prompt optimization to overcome the limitations of traditional prompt optimization. Our goal is to create system prompts that are adaptable to various user prompts and tasks. We view this as a bilevel optimization problem because there is a hierarchical relationship between system prompts and user prompts. The system prompt needs to work well across different tasks, which is our higher-level goal, while also aligning with user prompts that are tailored for specific tasks, which is our lower-level goal. We aim to find the best system prompt, starting from an initial version, that enhances performance across a range of tasks. This involves ensuring that it works well with user prompts optimized for specific tasks. To tackle this bilevel optimization, we use an iterative method that alternates between refining the system prompt and the user prompts. In each iteration, we first update the user prompts for individual tasks to boost their performance while keeping the system prompt fixed. Once the user prompts stabilize, we then update the system prompt by optimizing it across all tasks, taking into account the improved user prompts. We implement this process using meta-learning, which fits well with our bilevel approach. It allows the system prompt to learn generalization from task distributions while adapting to user prompts optimized for specific tasks. Next, we detail the meta-level system prompt optimizer, meta-SPO, which consists of two optimization loops. In the inner loop, we can use any existing prompt optimization techniques. One approach is to iteratively refine prompts based on previous mistakes. We start by assessing the current user prompt's performance on target task examples and identifying incorrect responses. To enhance performance, we analyze these errors and generate new candidate user prompts. We then evaluate the performance of these prompts and select the top ones that yield the best results. The outer loop operates similarly but focuses on optimizing the system prompt for a broader range of tasks. We first evaluate the system prompt's performance across tasks, identifying incorrect responses. We analyze these errors and generate multiple candidate system prompts. Finally, we assess these prompts not just for individual tasks but across the entire task distribution, selecting the top performing ones. We will now describe our experimental setups, including the tasks, datasets, models, and implementation details, and demonstrate the effectiveness of our proposed meta-SPO. To evaluate meta-SPO, we consider two scenarios that reflect real-world applications. The first is the unseen generalization scenario, where we apply the optimized system prompt directly to test time queries without further optimization. The second is the test time adaptation scenario, where we optimize user prompts using a few examples from the target task while keeping the system prompt fixed. Additionally, we explore two settings for optimizing system prompts: global, which aims for a generalizable prompt across domains, and domain, which focuses on tasks within a specific domain. Section Summary. In this section, we introduce bilevel system prompt optimization to create robust system prompts that generalize across diverse tasks while synergizing with user-specific prompts. Our approach employs an iterative meta-learning framework, consisting of inner and outer optimization loops, to refine both user and system prompts for improved performance across various scenarios. Section: Datasets. In this section, we evaluate the effectiveness of our optimized system prompts across 5 different areas, covering over 34 tasks. These areas include medical, which focuses on answering health-related questions; review analysis, which predicts customer sentiment; reasoning, which tests logical thinking; grounding, which checks if responses are based on the given context; and safety, which identifies harmful content. For each area, we gather 4 source tasks to refine our system prompts. We then use a varying number of target tasks: 4 for medical, 3 for review analysis, 3 for reasoning, 2 for grounding, and 2 for safety, to assess the prompts, ensuring these tasks were not part of the optimization process. We utilize Llama 3.2 as our base model for generating responses and GPT-4o Mini for optimizing prompts. We set the temperature to 0 for the base model to maintain consistency and to 1 for the optimization model to introduce variety. Our meta-SPO process involves 3 iterations of both inner and outer loops. We create 9 different prompts for system optimization, keeping the best one, and generate 3 for user prompts. During our analysis, we use incorrect examples to guide the optimization process, running each experiment 3 times and reporting the average results. We first present the performance of our optimized system prompts in scenarios where target task examples are not available for optimization. Here, we find that meta-SPO consistently outperforms all baseline models. We visualize the performance of a randomly selected 20% of user prompts using the optimized system prompt, revealing that 85% show improved results with meta-SPO, demonstrating its effectiveness across various user prompts. Next, we explore the relationship between the similarity of source and target tasks. We hypothesize that greater similarity leads to better performance. By measuring this similarity and correlating it with performance improvements, we find a positive correlation, indicating that while similar tasks are beneficial, Meta-SPO still performs well even with low similarity tasks, showcasing its ability to generalize knowledge across diverse tasks. Finally, we test Meta-SPO in a more challenging scenario where there are no overlapping domains between source and target tasks. We optimize prompts using tasks from 3 domains and evaluate them on entirely different target domains. Our results show that Meta-SPO consistently outperforms baseline models, even when source and target domains are not closely related. We also observe that including more training domains enhances performance in cross-domain scenarios, highlighting Meta-SPO's robustness and the advantages of using a diverse set of training domains for better generalization. Section Summary. In this section, we evaluate our optimized system prompts across 5 domains: medical, review analysis, reasoning, grounding, and safety, using a total of 34 tasks to assess their efficacy. Our findings demonstrate that the Meta-SPO approach consistently outperforms baselines, showing robustness in generalization even across low similarity and different domains, while highlighting the benefits of diverse training tasks. Section: Results on Test Time Adaptation. In this section, we explore the results of our test time adaptation approach. We believe that the system prompt, optimized through our meta-learning framework, is beneficial in scenarios where user prompts for specific tasks are also optimized. This system prompt serves as a strong starting point, capturing knowledge from various source tasks, which can be adapted to user needs. Our findings show that the Meta-SPO method consistently outperforms other techniques across all domains, highlighting its effectiveness in test time adaptation. Next, we analyze efficiency. The system prompt from our Meta-SPO is crafted to adapt quickly to different user prompts and tasks. We visualize performance based on the number of iterations and data samples for test time adaptation, and our results indicate that Meta-SPO outperforms the default system prompt in all cases. Additionally, Meta-SPO is more resource efficient, achieving results similar to default with significantly fewer optimization iterations and less data. This suggests that our approach is practical for situations with limited computational resources and data. We also examine how the number of source tasks affects Meta-SPO's performance on unseen target tasks. Our experiments show that as we increase the number of source tasks, Meta-SPO's performance improves and becomes more stable, although the degree of improvement varies by domain. For instance, in the review analysis domain, performance increases by over 17% when the number of source tasks rises from 1 to 6, while the reasoning domain shows a smaller improvement of about 8%. These results indicate that Meta-SPO benefits from a larger and more diverse set of source tasks, especially when they closely match the target tasks. Furthermore, we analyze the roles of system and user prompts. We investigate whether it is necessary to assign optimized prompts to their respective roles by comparing 2 configurations: separated inputs, where prompts are assigned to their designated roles, and unified input, where they are combined. Our results show that the separated input structure outperforms the unified structure in most domains, except for reasoning. This suggests that modern LLMs perform better when the roles of system and user prompts are clearly defined. We also hypothesize that if the optimized system prompt provides valuable information, the model will focus more attention on it compared to the user prompt. To test this, we compare attention scores for both prompts across different methods. Our observations reveal that Meta-SPO directs more attention to the system prompt than the baselines, indicating that our optimized prompts effectively guide the LLM. Lastly, we conduct an analysis to see if Meta-SPO is adaptable to other LLMs. We test various models, including Llama 3.1, Qwen 2.5, and GPT-4o Mini, and find that the system prompt optimized by Meta-SPO consistently outperforms other methods, regardless of the LLM used. Notably, The prompt optimized for Llama 3.2 shows strong generalization when applied to different LLMs without needing further optimization. Overall, these results confirm that Meta SPO is effective across various LLMs, producing high-performing system prompts that maintain their effectiveness beyond the original model. Section Summary. In this section, we demonstrate that our Meta SPO framework effectively enhances test time adaptation by optimizing system prompts, leading to superior performance across various domains with fewer resources. Additionally, we find that the optimized prompts generalize well across different LLMs, confirming their robustness and adaptability in diverse scenarios. Section: Analysis on Meta SPO variants. In this section, we analyze the variations of Meta SPO. We designed Meta SPO to be very flexible, allowing us to use various prompt optimization components and their combinations within its bilevel meta-learning framework. For example, one variation involves executing only the outer loop without refining user prompts iteratively, which we refer to as the outer loop. We also have other variations, such as Meta SPO with APE and Meta SPO with EVO, which apply prompt optimization strategies in both the inner and outer loop stages. As shown in our results, the outer loop performs comparably to baseline methods but does not reach the full potential of the Meta SPO framework, highlighting the benefits of combining the inner and outer loops in meta-learning. Furthermore, the two variants, Meta SPO with APE and Meta SPO with EVO, significantly outperform the baselines, proving that our approach works well with existing prompt optimization techniques. In terms of qualitative results, we provide examples of the optimized system prompts. We notice that these prompts typically assign a more specific role to the language model, going beyond just being a helpful assistant. For instance, they may describe the model as a knowledgeable and analytical assistant tasked with processing and analyzing information across various topics, along with detailed guidelines or objectives.